Solo, please put it on the group that we will start. We will start. नहीं और नहीं तो ठीक है चलेगा वो थोड़ा खराब आएगा नो प्रॉब्लम इतना खराब नहीं है that board is looking fine in all the videos right so did you manage so please send me the link I have to send it to you. Yes, now it is on. Okay, so we can start, and I need 2 volunteers to play one game. Okay, one volunteer is okay. Sorry, one volunteer. The other one will be me. So who is it? You raised your hand.
Yeah, sure.
So the problem is you don't know the game. So the game is like there will be a bunch of crosses on the board, okay, and these are called open points or open tips, and then these things you have to, in any move you can just connect 2 open tips. It can be the same cross, and then you have to put a crossbar here. And then another thing you have to maintain throughout the game is that you cannot cross 2 lines. So you cannot cross an existing line. Okay? And then whoever cannot give a move first loses. So now you choose, it's a 2-player game. We move alternatively. Okay? So you choose which player you want to be. You want to be the first player. So let me cheat. So we do it with 2 crosses. We can pick color. Okay. So you are second, you are? First player, yes. Yes, otherwise I will. So I'm very good at this game. Okay? So don't think too much, just play.
I know I have well lost definitely.
I will. Okay. So, yeah. My turn, your turn. You can use these also. Now these are also allowed. Yes.
So I can use this like that?
Yeah, yeah. But you have to put a crossbar to finish your move. Okay? 2 moves. Third move. 4th. That's a small one. 5th. Then 6th. No, I think it's 7 moves, right?
Already? You were supposed to. You didn't start, that's why.
Huh?
You were the second player when you started.
I am the second player.
No, you were supposed to.
I'm the first player. No, you were the first player, right? No, he wanted to be the first player. So he will play again. He will win. Right. But you are supposed to be the first player. That's okay. You can win. No, you can win. I don't mind. You win. I have been winning this for a long time. So now you have 8 moves. Okay? Congratulations, you have won. You can check that there is no other move, right? Okay, thank you. Yeah. So now the thing is that we are going to speak about planar graphs, right? So what are planar graphs? I will just for the record I will write the definition. Planar graphs. Graphs that can be drawn on a plane or a sphere, it's the same thing. Without its edges crossing. It's a very simple definition, quite intuitive. I think there were many games we used to play, pen and paper game when we were kids, which will have such conditions that you cannot cross. So, planar graph, as Florent told in his first lecture, is also a kind of sparse graph, and what Hermander told, it has a very strong relation with treewidth, especially if you allow like excluded minors. Where is Hermander? Okay, he's around. So what we are going to do is, the main theme is planar graphs, so we will continue with that, and then at some point of time I will speak about coloring, because coloring is some important aspect of planar graph. And in between I will just mention some topics without telling any details about it, so that you know it can be expanded like that. So for example, here I would like to mention something called, this is zero crossing, right, for planar graphs. But there are families of graphs where you allow 1 crossing or 2 crossings. So that gives you the theory of crossing number. Okay, just mentioning the name, nothing else. You can search and see. Janos Beck is someone who frequently comes to India and works on this. Okay. Now, for planar graphs, I want to tell you that, well, I was very stupid and he won because of this. He did not play first, I played, I was still here. But I will tell you why I knew and how I knew. For that, we will need to prove something called the Euler's formula for planar graphs. So, for connected planar graphs. So I will say G is a connected planar graph. Then we have this kind of thing. Then G minus EG plus F of G. So I also need to tell you what is F. So F are the faces, but I think all of you are familiar with the, is there anyone who is not familiar with planar graphs? Then I can experiment a little more, or otherwise I go on.
I don't know.
Okay. Okay. So for you, one question is this graph planar? No. Look at the definition. The most important part of the definition is probably this, that it can be drawn. Okay. So I can draw it because I can just erase this and draw it from outside. So it is planar. And then, because the cycles of the planar graphs are closed curves, they will divide the whole plane into two regions, into something called Jordan curve theorem. And one will be inside, one will be outside. So these inside parts, they are basically the faces. So you have one, not inside, not only inside, like inside and outside. So this is another face. And then you have a third face here. And a fourth one, which is the unbounded outside face. Okay? And next, something from topology. So I have written it's a plane or a sphere, right? So actually they are exactly the same definition, even if I replace plane with sphere. So suppose this whole floor is a big bed cover, and you have drawn the planar graph on this. Now what you can do, and you have drawn with a bad pen, so the impression is on the other side also. So now you take these sides of the bed sheet and gather it at one point, so it becomes like a sphere, but the planar graph is drawn somewhere, right?
Stereographic projections.
Yes, exactly. And the other way around, if you take a football and draw your planar graph on that, then somewhere inside a face, you puncture the football and stretch it to the corner. So now the planar graph is drawn on a plane. So it's either plane or sphere, both works. Okay. Now what are we saying? Take any connected planar graph. Now take number of vertices minus number of edges plus number of faces. It's a constant. It's 2. So how do we get that? The proof is
that you want to take a drawing of the planar graph and then you have some faces to come.
yes. You have to take a planar embedding. Otherwise, face doesn't mean anything. So you have to take a planar embedding, which is the drawing on either a plane or a sphere. And it is also, if you fix a drawing, so planar graph with a given planar drawing, that is sometimes called a plane graph also. So I may use these terms. And if I am speaking about faces, you know my planar graph is actually a plane graph. I have fixed a drawing. Okay. Now the thing is, yes?
As you know, we say it can be drawn on a plane, so it is a planar graph.
Yes.
Is there any significance we are talking about? It can be drawn on a sphere.
Yes, we'll come to that after some time. Okay. So, and maybe in tutorials. So, the proof is very easy. It's by induction. So, let's say Vg equals to 1. And now I'm allowing also multigraphs and graphs with loops, okay? Because this formula is very general. So for Vg equals to 1, you take just one vertex. What are the values? Tell me. How many vertices? 1. How many edges? 0. How many faces? 1. So I have 2.
There can be loops, right? So
Yes, next. Now, with one loop, so what happens to this? Vertex stays as it is. Edge is incremented by 1. Faces, now you have 2 faces. So this is also incremented by 1. So plus 1 here, plus 1 there. Stays constant, plus minus. Now you have multiple loops. K loops, let's say. Okay? So how many vertices? Still 1. How many edges? K. So it's K. And how many faces? K plus 1. It's still 2. So it is proof for the base case. Number of vertices equal to 1. Now, by induction hypothesis, you think it works for some n vertices or k vertices, okay? Or no, a vertex is always n. So n vertices, and we want to prove it for n plus 1 vertex. This is a n plus 1 vertex planar graph, this potato, and then, oh, this is French way of saying it, right? And then you take, of course, it is a connected graph, so it has at least one edge. You take one edge. It may have some common vertices, some other things, several other things. But this edge is special. I call it UV. What I do is I contract them. So what does contraction means? Contraction of UV is replacing U and V, both the vertices, with, let's say, Z, such that if X was adjacent to U or V, X is also adjacent to Z, and with multiplicity. So if it was adjacent to both, then you put 2 edges, okay, for now. So here what will happen if so I will make this big vertex, which is Z. I have contracted them. So let me just it will look like this, right? Okay. Now, this graph, let's say, is G, and this is G prime. Okay? So let's do the calculation. So I think I have to erase this too. Yeah. No, but I actually want to keep it. Let's see. Until I prove this formula and apply it. So for G prime, so I can write VG prime minus EG prime plus FG prime, right? But what I actually want to calculate, and I know this is true because of the induction, VG prime has n vertices, right? I have deleted UV and actually I have squeezed in, I like to visualize it, even though the definition is deleting and adding one vertex. It helps. And I want to figure out what this is. I'll be happy if this is 2 and then the proof will be done. Okay, so this was N. Edge was something, let's say E. F was something, let's say F. This I know is N plus 1. How many edges are there?
E plus 1.
E plus 1 because I have destroyed one edge in the process of contraction. So E plus 1. How many faces are there? F. Because no faces are destroyed. I have kept all the edges, right? All the closed curves. So now this 1 and 1 cancels out and I exactly get that equation. So this is indeed 2.
It will be E minus 1. Because one is disconnected.
No, this is G prime. So in G prime there is one less edge and I am coming back here. So it is E plus 1. So this plus 1 and minus 1 gets cancelled out. Just to say this is cancelled out. And I get 2. So this is the proof of Euler's theorem. Is that okay for everyone? So after every proof I will probably ask this. And
Sir, we are assuming that contraction preserves planarity.
yes,
Is that easy to see or?
it is easy to see because you are not creating any crossing. Intuitively it is easy to see. Is there a proof of that? I never did a proof of that. I can do it with topology maybe, but
It's like we are increasing number of edges.
we are never increasing number of edges, but we are not doing anything like which will create a crossing. Yes, sorry. We can.
Suppose you contracted and then there is a crossing.
Okay.
And you can open up that edge. If that crossing is, because it is a.
Okay. Then it will still remain a crossing. Okay. So that's a good. Yeah, again, still he can ask if we move around the points, we'll need to maintain planarity. It is easy to visualize, but to formally prove it will need topology. Like this. Okay. But anyways, I think we can be convinced that contraction preserves planarity. Sorry? What if there are loops? But what I'm saying, this edge is not a loop. Because it's a connected graph and I have at least 2 vertices. So there is an edge which is not a loop. I'm contracting that edge. And then the loops will remain loops. I mean, even if you had a loop over here, it will just stay as it is. Okay.
But the edge we are contracting
Is not a
should
loop.
not be loop.
Yes. That's easier. Okay. That's fine, right? Now let's go back to Brussels sprouts. So this game is called Brussels sprouts because the crosses are like projection of Brussels sprouts, somehow. But there is another historical reason.
There are multiple edges between U and B, then they are not.
Yeah, you contract one, no problem. Then you create a loop. Okay. Even if you have like this one, then you create exactly a loop here. So faces stay the same. Okay, good. Now I'm going to erase that part. And let's say what happens for Brussels sprouts. So this is an application to that. So let's say I have started with n crosses and game ended in x moves. Okay, the game has ended after x moves, let's say. Now I want to find out what are the possible values of x. If I can say, as you can guess, it will be of a certain parity, and then I will know. Okay. So at the end of the game, or at any point of the game, this is a planar. But at the end of the game, it must be a connected planar. Okay? And these guys are like vertices, the connections are edges, These are just there, but they will be useful, and there are some faces also. So, how many vertices do you have? That's a small v. So I started with n crosses, right? In each step, I have added one extra vertex. So n plus x. Yes, x plus n or n plus x. Okay. Now, how many edges are there? How many edges are there to begin with? Only some crosses on the board, right? 0. In each turn, I have added 1 and subdivided it. So in each step, 2 edges are added. So in x steps, 2x edges. Now the number of faces. Number of faces is a bit difficult. Okay? So imagine this scenario. You have a face, but you have 2 open tips inside it. Yes?
You added 2 vertices in every iteration.
Sorry? Say it
You
again.
added an edge.
Yes.
Was it like 2 vertices? You introduced 2 vertices in each.
No, only one vertex. So when I do a crossbar, only this middle thing becomes a vertex with a possibility of an edge from top and a possibility for an edge from bottom. But now imagine this scenario. Some face has 2 open tips. Will the game end? No, right? Because you still have a move left. So you cannot have 2 or more open tips inside a face. So you have 1 or 0. But can you really have 0? Because suppose you have just nothing, no open tips inside. But then how did the face get created? At some point of time you must have added the last edge to create this. And then you had to give a crossbar, so at least 1 tip will be inside. So at the end of the game, whatever is the number of open tips, that is the number of faces. So face I can say is number of open tips. Okay? But how many are the number of open tips? What was the number of open tips in the beginning of the game? 4n. N crosses, each had 4, so 4n. And in each move, what did I do? I closed 2 of them. I created 2 new. So it remained constant. So even after x moves, I will have 4n open tips. Now it becomes easy. Plug it in the Euler's formula. So n plus x minus 2x plus 4n equals to 2. That will be x equals to, please cross check, I am writing from memory. So 5n minus 2. Okay? So whenever you have odd number of sprouts on the board, number of moves is odd. And the game will end after odd number of moves, right? Whenever you have even number of crosses, so the first player will win, because first player will have the last move. And whenever there are even number of players, the game will end after even number of moves, and the second player will win, which he did. Okay, so this is one application. Okay. Then I wanted to bring a football. I could not find it. But let me see the time. I may actually skip that part. Yeah, I will skip that part. So there is a nice application how you can figure out very symmetric tiling of the sphere, but it's a bit diversion from the topic.
One question about this.
Yes.
So, is there a characterization of the graphs that we obtain in this game? It's like degree at most 4.
Yes.
But
Degree,
is there a,
degree I think will be exactly 4.
at most
No?
4?
No, at most some are 2, right? Okay.
But is there a
No, there is no characterization. But what is known is this game ends exactly after this. So no matter what strategy you use, how you play, it will be these many moves. Yes.
Suppose for
for some n, the player 1 will win. So
Yes.
no matter how it, like whatever strategy you will
Yes.
for one.
No, whatever strategy you use, because the number of moves is a constant when the game ends. Okay, but I will tell you some context about this game and then move on. So the context is, there is another game called Sprouts, which is the original game. This is kind of a imitation of it. So in Sprouts, what you have, you start with dots instead of crosses. And the rule is that you can add these or loops and you subdivide. Okay? You can add loops also. And the second rule is you cannot go beyond degree 3 for any vertex. Okay? So you have to, maximum degree can be 3. So for example, if I do this, then this guy is done. I cannot do anything anymore. Maybe here. Something. But this goes on. Okay? Now there is a conjecture called Sprout's conjecture. It says first player wins, has a winning strategy if and only if n is the number of dots you started with, n is 3, 4 or 5 mod 6, and second wins if n is the rest, basically 0, 1 and 2 mod 6. Okay? And this is wide open. Like they have computer check until 50 or something. There is not even a strategy how to attack this game. Just to tell you how planarity can be very difficult.
This conjecture in which year?
Which year?
Yeah.
No, it's quite in the 70s, maybe 60s or 70s.
Still,
Yeah, still wide open. I mean, nothing has been done. Yes, yes. So, first has a winning strategy, basically. So, in a two-player game, one of the players must have a strategy if it is a finite game. And this is a finite game, also impartial game. So, someone has a strategy, and the first player has strategy if n is of that type. Otherwise, second player has a strategy.
conjecture is 1991.
1991, okay. It's more recent. Thanks, thank you. Okay.
For specific values of n strategies.
Yes, so for until something around 50, they have done a computer search and saw that there is a strategy for, according to the context. And until 7, someone has done a hand check, in fact. 50 pages long case analysis. Okay. Now, let me go to the next topic. Oh, actually, this is what, I will come back to planar graphs again, but first I also want to speak a bit about coloring, okay? And then I will prove some properties of planar graphs using the Euler's formula. So, let's speak about coloring. So, does everyone know what is coloring? I will define it in this. Yes? Okay. Good. So, K coloring of a graph G, it can be defined in many ways. I like this formal one, is a function C from vertices of G to, if I have said K, so I will actually fix the colors because you can take any set of colors, but I usually fix the color for convenience. K, such that the only condition is U is adjacent to V will imply C of U is not equal to C of V. Okay. This is what coloring is. So since all of you know coloring, now I will speak a little bit about history, maybe. Yes, let me speak a little bit about history. So, or some examples. Let's do some examples. So how about you color an independent set? How many colors do you need? Just one. Okay. How about a tree? Okay. Because you can just do 1, 2, 1. Right? Okay. How about a 5 cycle? 1, 2, 3. I could have used 2 here. So, sorry, I could have used 1 here and 2 here. But then here I have to use 3. Right? For all odd cycles it will be 3. And for all even cycles it's 2. Okay, fine. Then maybe do a little more complicated here. How about this one? How many vertices? 10 vertices. How about this one? Okay, so I will complete what I wanted to do. Okay, now, how about this one? So at least, at least 3, because there is a 5 size. Can you do it with 3? Is my question. Let's see. See, 1, 2, 3 I have to do because I have to use 3 colors. I cannot use all colors twice. At least one color I have to use once and the others will be 2 times. So I have to do this. Then, how about this one? It has to be 1. This one can be 1 or 3. How about this one? This has to be 2. And then can you find me something which should, this, how about this one? This has to be 3. So I need to use the 4th color here. So it's at least 4. Notice one thing, this doesn't have a triangle. Okay? Okay. Maybe another example will be, I should say something else which you already know. So that is chromatic number. So chromatic number chi g is the minimum k such that g has a k color. Okay? And we are trying to color with minimum number of colors. It's a minimizing problem. So, trivial thing. And we always take simple graphs because with loops it's impossible to color. You cannot give itself a different color. And with multiple edges it's redundant, whether we put one edge or many. So how about the complete graph, Kn? How many colors do you need? N. So it is kind of an obvious obstacle. If you have a complete graph sitting inside your graph, then you cannot color it with using like less than n colors, right? So that is called click number. So what is click number? That the biggest or the largest complete graph that is a subgraph in your graph, that number, whatever the cardinal is called the click number. Okay. So omega g equals to max n such that Kn is a subgraph of G. Okay? And this is called click. Okay. basic what we want. The language is done. And next, what I want to move on to is a bit of history, and then we will look at some proofs. Okay. Okay. Here I want to keep a tab of what we did. We did Euler's formula. Now, this Euler's formula actually comes from topology. So now your question, who asked this, why this sphere? So you can have a Euler's formula on a sphere if you draw the graphs on a sphere. But if you draw the graph on, let's say, a torus, is this idli-bara kind of a shape. So if you draw it on that, then you will get even more graphs than planar graphs. You can draw all the planar graphs, definitely, but you can get many planar graphs. These are surfaces of genus 1, orientable surfaces of genus 1. And then there are surfaces like projective planes. So projective planar graphs will be non-orientable, it's a non-orientable surface of genus 1 still, right? And sphere, sorry? Genus is like, in torus you have one hole, and then there will be many holes. So that is kind of what is called genus. But this is not something I'm going into details with. Okay? So that gives you another topic of study, which is the graphs on surfaces. Surfaces. So this parameter is called the chromatic number. Okay. Now, I want to define the chromatic number for a family of graphs instead, and in fact click number also, but I don't care too much about click number right now. So let, or somewhere else where I can keep it, let F be a class of graphs when we define chromatic number of F equals to maximum chromatic number G such that G belongs to F. Okay. Sorry, I squeezed it. But it's kind of the worst case scenario. When we ask the question that how a family of graphs can be colored, I'm looking at actually the worst case scenario. Okay? That what is the worst graphs in that can be colored with certain number of colors. Now the question comes that what is the chromatic number of certain families of graphs? Whether it is bounded, if it is bounded, then by what? So one of the questions which did not come from graph theory, or rather maybe graph theory came from it. So that is the 4-color conjecture, which basically asks what is the chromatic number for the family of planar graphs, right? I want to erase this also because I want to have multiple segments. Okay, good. I think I passed the this time quickly because these things is a bit of repetition for you guys. Okay. I forgot some dates. 4 color theorem, conjecture. Also 4cc. When is it? If you can check the dates. 1958. 1858. 58. Yes, something like that. Yeah, I will trust him. You should have been a historian or person from Euler. He is awesome with dates. Okay, and this is by someone called Frank Guthrie, something like that. And he was a cartographer, not a graph theorist, and then he passed on it to his mathematician friend, who gave it to wrote to some famous mathematician, and then it became a very intriguing puzzle for everyone, and people could not solve it. In fact, Haywood solved it, and after some 10-20 years, so it became the 4-color theorem. So now you guys are thinking I'm saying something wrong. So you are right, partially. Haywood.
Maybe you should state the conjecture also.
Yes. Planar graphs is 4. Okay. So the chromatic number of the family of planar graphs is 4. Okay. But then Haywood proved it, and after 10 years, Kempe found a bug in his proof. And then Kempe fixed it, but could not fix it completely. So it became Kemp gave the proof and Haywood proved it. Sorry, yeah. So give the proof, and then so I prefer to keep both names, and then it became the 5-color theorem, which says that chromatic number of, so I will use some symbol for this. Okay? For planar graphs, I will use this kind of a symbol, script P kind of a symbol, something like this. This is less than equal to 5. So he proved the upper bound, and the lower bound is obvious because K4 is planar, so it cannot be less than 4. So Haywood gave a proof. This one we will prove at some point of time, and then later on Appel and Haken. Actually, we have the dates, I guess, somewhere. Yes. So. (1976), so they said that yes, indeed, this is equal to 4, and then later on, so this is this proof is through discharging method, and it is a kind of a very strong technique. Okay. However, that discharging technique is kind of a big brother of whatever Kemp and Haywood used. So we will learn this one, and then we will learn discharging technique, but not, of course, not this proof. It's horrible. Like horrible in the sense it's huge, and I don't know the proof. And then later on, Seymour's team. So it's Robertson, Sanders, Seymour, and Thomas in 2005. They simplified the proof, but still it is computer aided. But the number of configurations they check are less. Okay? So this is kind of one part of the history. I will simplify this a little bit so that it takes less space. So here it will be 5. Okay. There are several variations of coloring, by the way, like fractional coloring, least coloring, edge coloring. There have been attempts to prove the conjecture in those lines. For example, for edge coloring, there is an equivalent formation. Not going into that, too much in fact. And then, for the 5-color theorem, this guy, Thomason has a very small proof. It's actually one paper which is, with reference, it is less than 1.5 page, with title, reference, everything. And the proof is that small. So maybe at some point of time or in the tutorial I'll do it. But it says something stronger than this. It doesn't bound the chromatic number, it bounds the least chromatic number, or choosability, and that is that has some added constraint. So that implies the 5-color theorem as a corollary. Anyways, so this is kind of the story from the 4-color theorem, but I think I should add one more thing here. I keep forgetting the spelling. Then there should be a Z. No, TZ, right? TZSCH. Yeah, good. So, what does it say? It says that chromatic number of, I will say P4 is equal to 3. So what is P4? This is triangle-free planar graphs. Why I wrote 4? Because the smallest cycle size that we allow is 4. So I'm saying planar graphs with girth 4. Okay? So what does Groth's theorem say? They say if you have a planar graph and if it doesn't have any triangle inside it, then I can color it not just with 4 colors, I can even color it with 3 colors. Okay? So if you go around the map of India, put vertices inside each state, and the neighboring state you put edges, I have checked it's a triangle-free graph, and you can color it with... No, it is not a triangle-free graph, but you can still color it with 3 colors. Okay, it's a 3-colorable graph, which is not triangle-free. So there are many not having triangle, sorry. So this is not the full characterization, is what I'm going to say. That's probably also obvious, because triangle itself has 3 colors. But anyways, so this part is about planar graphs, and now I want to move on a bit away from planar graphs and focus a bit more on colorings, and have another column here. So all of you have studied coloring. What theorem does come to mind when I speak about coloring? What kind of a general theorem? Brooks theorem. Okay. So what does Brooks theorem say? Yeah. Now I need this. So consistent. Brooks theorem. What does it say? So chromatic number of G is less than equal to delta of G. Delta is maximum degree, unless, and G is connected. So unless G equals to Kn or odd center C 2n plus 5. I need not be done. No, I think we have to say about components, right? Every component. Then I have to say G doesn't have a component of this size, because you can, because you can put a big Kn and then very small many graphs, and then still the delta plus 1 will be achieved.
We need one component is equivalent to for doing
Yes, but to be technically correct, I have to say that. So otherwise here I have to say G has one component which is like, so just simplify it by saying G is connected. And G is connected. Okay, so Brooks theorem, you studied in class. What about after that? What is the next step? See, what Brooks theorem did is, it told us, of course, odd cycles are one exception, but apart from that, if you don't have a very big click in your graph, then the graph can be colored with less number of colors, right? So that's where the next thing comes. Again, a conjecture by Borodin and Kostoshka. And I have the year for this, 1977. What does it say? It almost says what I told, but there is a little bit of. So if the maximum degree is greater than or equal to 9, and the omega of G is strictly less than delta, so I will say less than delta minus 1, okay? So delta is always maximum degree of G. I'm not writing delta G all the time. This implies that the chromatic number of G is less than or equal to delta minus 1. So I gain 1 if I exclude another click, right? So I gain 1, and not only, with some exceptions. It doesn't work for delta equals to 8. There are some, so basically this doesn't work for delta equals to 2. It works for delta greater than or equal to 3. This one works for delta greater than or equal to 9, okay? It is the claim, so it's a conjecture, so it's a claim. And then there is some very good theorem by Reed, which says that this conjecture is true for delta greater than or equal to not 10, 10 will be too good, 10 to the power 14. Okay. So, but then in the same paper, and I have the date for this also, 1999. Okay. In the same paper, Reed comments that, our calculations are very loose. So if you have the time, and it's not a quote, I am saying it what I remember. So if you have the time and energy, you do it, tighten the calculations, and we think that this can be improved to 1,000. That would be great, So, and it uses probabilistic method. So those who are good with probability can probably try it. So it can be one really excellent open problem to think about. Okay, but it doesn't end here. Reed not only, proved this, he also conjectures something. You see, somehow the Brooks theorem and Borodin-Kostoshka conjecture tells us there is a trade-off between delta and omega. Click number and the max degree, and probably the chromatic number can be bounded by a function of them together. So that's what Reed does. So what Reed does is says that current G is less than or equal to delta plus 1 plus omega of G, the average of it. So he's saying the chromatic number is bounded by the average of this. Okay? So average of maximum degree and omega, but there is a plus 1 also. So that would be a very nice thing to prove, because clique number is the obvious obstacle, and delta kind of gives me, because of the Brooks theorem. Yes.
So by this conjecture of Courcelle,
Yes.
so then by the result that there are regulatory graphs, for example, that have unbounded information,
Yes.
then this implies that those graphs have maximum degree unbounded.
If you prove this, no, it's the other way around, right?
So this says that
So, if you're
if the
basically if you don't have a very big clique compared to your delta, so in any graph, the biggest clique you can have is of delta size. Sorry, delta minus 1 size, right? Because maximum degree is delta.
Delta plus 1.
Uh,
Unless you avoid this.
Delta plus 1, yes, yes. Delta plus 1 clique.
That comes only
So-
when there's a single click.
Right. So in a connected graph. So that one, that very big clique, that is delta plus 1, is excluded in the Brooks theorem. And we are saying if you move that out, then your graph is delta colorable. Otherwise you need delta plus 1 colors. I mean, see, odd cycles are there, but it's small clique, right? And then you are saying that, if you not only remove delta plus 1 cliques, you also remove delta cliques, delta size cliques, then it can be colored with even less colors, that is delta minus 1 colors.
yeah, so it says that if the maximum degree is at most delta minus 1,
Yes.
then the
No, maximum degree is always delta. This is clique number. This is clique number. So this is the biggest complete size of the biggest complete graph in the graph.
yes.
It's
So the conjecture graph that is at most 2, right?
at most 2. Yes.
And conjecture graphs that have unbounded information.
Yes.
So then what is the, can you relate this?
I think it is a bit difficult to relate with that. With this one, you mean.
Because here we are
With this one.
Because here we are giving some implication that if the clique number is bounded, then the chromatic number is bounded,
Yes.
right?
But if you put this equal to 3, yeah, I think it's better understood here, someone. So if you put this equals to 2, then the delta has to be very high for the chromatic number to go high. So I think it's better understood there. It's kind of a generalization. Okay. Is that okay? And anyways, after that, again, Reed only he himself did some proof of this, proof that this conjecture 3 holds for large delta. So I actually do not know how large, but something 10 to the power something. And then also, if the omega has some kind of a bound, so that is 1 minus 7 by 10 to the power 7. So it has a bound. The omega is bounded by some factor of delta. Okay? It's not just delta minus 1 or constant, but it's a factor of delta. Okay? So then a series of work started. So actually, people now started to do things like this. So they started to prove theorems like this. That chromatic number of G is bounded by 1 minus epsilon times delta plus 1 plus epsilon times omega. So people started proving these kind of statements, and they're trying to prove that this epsilon, they're kind of trying to improve this epsilon to half, because if you prove that to be half, that will improve, right? Okay. And what if you put omega to be delta minus 1 over there? No, that doesn't mean it. Sorry. So, no, it means it becomes delta, right? So if you put omega equals to delta minus 1, then it becomes 2 delta and it cancels out, it becomes delta. So I think from there you can get this one. With some, there are some delta constraints everywhere.
So this is rho bar with epsilon?
This kind of epsilon. Something along this epsilon, but I am not quoting, I am not translating this one. There have been improvements. I'm going to list them. So the improvements are epsilon equals to 1 by 320 e to the power 6, and this is by, I may have less space here, let's see. So King and Reed from quite recent compared to the previous things, it's 2012, okay? Then the next one is from some student who did PhD along with me and Florent, not in the same place. Florent can guess who it is. This next breakthrough is huge. It is just 1 by 26, no tricks and no powers after that. Okay? So that is by Marc Bonamy, Perret, the double P, and Luke Poster. And this is from 2016. So actually it's not 2016, but the archive paper came at that time. Okay? And where should I extend this? Maybe in the right side. And after this you go here. So then 1 by 13. Again, Luke Postal. This is 7. And then the last one, the best known, is 1 by 8.4. And this is Hurley. And Kang. This is something like 2020 plus. I'm not sure if it is published yet. It's probably still in the article. But however, it is this number. So I'm not entirely sure, but I think all of them uses probabilistic methods. I haven't looked at everything, but to the best of my knowledge, they all uses probabilistic method, and you see many improvements happen very quickly in a quick succession. So maybe it's a good idea if you want to work on this, you can read these papers and see. Okay. Good. Now the last one. Maybe that space is good enough. No, two more history, and then I will go to proofs. Okay. So this is kind of one set of it. This is the next set, and I have two more. Okay. So this coloring concept kind of generalizes through homomorphism, which is also my research area, but I really need to say this notion, and you'll know in the next lectures why. So G admits a homomorphism to H, and I call that homomorphism F. If F is a function from Vg to Vh such that if U and V are adjacent in G, then, or if this implies that f of U is adjacent to f of V in H. Okay? So if you satisfy this condition, then it's called a homomorphism. So you see, instead of taking a function from vertices to colors, I'm actually mapping it to another graph. Okay? So that graph may have certain structures, but when I actually did it for coloring here, I have erased it now. You could have taken a complete graph on k vertices. Okay? That will be taken. So homomorphism is a bit more. Okay? But why I wrote this is because what you can say is, I will again write this. SCH. This theorem actually becomes that P4 maps to C3. So all planar graphs having no triangles, they actually map to C3. C3, K3, they are the same. However, now there is a conjecture which is in network flows originally, but it has a dual, equivalent dual. So I told you that 4-color theorem has a dual formulation using edge coloring. So network flows are some problems which has weights on edges, and it's basically on that. But it has a dual formulation using homomorphism. Okay? But whatever this conjecture is called by the name of its author, Jazier from 1982. Whatever this conjecture is, it was disproved. Okay? But then, if this conjecture is restricted to planar graphs, so I will say Jazier, but with a star for planar graphs. Okay? So, if this conjecture is restricted to planar graphs, still it remains very interesting, and that's a big open problem. So Jazier's conjecture restricted to planar graphs, what it claims is P4K, I will come to that, maps to C2K plus 1. So what does it mean? It means a planar graph who doesn't have small cycles. So the smallest cycle, or the girth of the planar graph, is at least 4K. Those kind of planar graphs. So you see the planar is already sparse, and its becoming more sparse because you have put a girth restriction. So that's why this sparse theme comes. Okay, this is for planar graphs which are sparse. This is bounded degree which are not so sparse, but a very rough parameter. The first parameter you can think of about sparseness. Now you have planar plus girth. It's very sparse, but anyways, I mean, Bloch may not agree with the very sparse thing, but it's sparse anyways. Okay. Now it is this, and then there is a second conjecture, which is J. Zhang. Is there an H? Yes, it's correct. It says, well, I'm going to write exactly the same thing right now, but then I'm going to change it a little bit. So it's the same, but I will write O here. What does it mean? So odd girth, odd girth 4k plus 1. 4k plus 1. Okay. So what it says is, so planar graphs without any small odd cycles, you can allow even cycles, no problem. Okay. So the second conjecture is stronger. It says that I don't care if my planar graph has small cycles as long as they are even. But if they're odd cycles, then I want the odd cycle to be at least 4k plus 1 size or more, and then I'm sure it maps to C2k plus 1. So all these things also actually tells us that there is a parameter called circular chromatic number, which is quite important. And in circular chromatic number, mapping to C2k plus 1 corresponds to having circular chromatic number 2 plus 1 by k. Okay? But let's not go into that. Let's take that this is our conjecture, and let's look at the progress that has been made recently. So maybe I will not write too many names, okay? So for the first one, the progress made is, so basically, instead of this, if I have G, okay? If I have G instead of this, for which G it works. Okay? So instead of 4k, I will have a higher value, and for those families, people have proved that it maps to C2k plus 1. For which G? So for G greater than equal to 10k minus 4. This is by Neshatril and Zhu. The year maybe is more interesting, is 96. Okay? And then for G greater than equal to 8k minus 4, that is only Zhu. This is 2001. And then a bunch of people, 20k minus 2 by 3. This is by Borodin, Kim, Kostoshka, and Douglas West. This is from 04. Okay? So they have this kind of progression. And I know the last one is using discharging method. This proof I know. I have. The others, sometimes they have used discharging, sometimes they may not have. Okay. And then there were some improvements here also. See, these things are not improvements here, right? Because I can have small cycles here. Now, but any improvement in this will also improve those results. So the best known result, general result, is G odd greater than equal to 6k plus 1. So this is odd girth. G sub O is odd girth. And this is by Lovas, Thomason, Wee, and Zhang. From 2013. Okay? So this is the best known general result, that if you replace this 4k plus 1 by 6k plus 1, I'm not able to capture everything, but still very nice improvement. So then it works. But a bit more. So those are general improvements. I'll make a small thing here. So if k equals to 1, what does it say? So no odd cycle of size 3, right? So it becomes P4, P4O, because there is no odd cycle anyways, loop is not there, so P4 goes to C3. Exactly the gross cycle. P5 goes to C3, yes, but I allow PO5. No, I mean, it is PO5, I allow even cycles, so it is essentially P4, because I am allowing 4 cycles. Only exclusion is triangles, so it becomes P4. That is exactly the Grotch theorem. P4 goes to C3. Right? The very first case gives me an extremely non-trivial theorem. So the Grotch theorem classical proof is much more difficult than the 5-color theorem classical proof, for example. Yes?
This significance of homomorphism is that we can bound the chromatic number of G in terms of chromatic number of
Yes, yes. Chromatic number of G is less than equal to chromatic number of H.
Yes. Roughly how this is because there would be
Yes, because you take another homomorphism to k, and then homomorphism is transitive. You can compose those functions and it still remains homomorphism.
because we are not saying that the verses of G will be mapped to the distinct verses of in H.
Yes, doesn't matter.
How this
Oh, okay. That is the question. So what I'm saying is, whenever you have an edge, they map to distinct vertices. Because this graph is a simple graph also. It doesn't have loop. So I am coloring G with the vertices of H with the condition that adjacent vertices of G do not map to the same vertices of H. That is exactly the condition of coloring. So number of vertices in H is a bound. Okay. So k equals to 1, this is this. I'm not writing the spelling once more. So for k equals to 2, what should be the bound? Here? So what should be the number? So k equals to 2, what should be the number? 9, right? But not in the conjecture, sorry. In this. So what is proved? For k equals to 2, what is proved? So 13, right? But then Luke Postel has something better. They have proved for k equals to 2, they have proved for G0 greater than equal to 11. Okay? And then for k equals to 3, it should have been 19, but they have proved for GR greater than equal to 17. And for, I will stop here, so this is okay, 23. Okay? So it's very small, but you can check later on. Okay, so yes?
Can you just write it a bit bigger? It's not
Yeah. These places, so basically, what I want to say is that the problem is where should I want to keep all of them, right?
No, but it's not just visible in the video. That's
Okay. I'll try. I don't know if there is enough space. Maybe go here. But that also I want to preserve for something else. So, yeah, when I do the proofs, it will be bigger.
And please use a white chalk. Okay, sorry.
I think whiteboard.
This one. Let that stay. So I will give it to you in written. Maybe. So k equals to 1, it's the Grotch theorem. and then k equals to, I don't think it's making a big difference. So g0 is greater than equal to 11, k equals to 3, g0 is greater than equal to 17, and k equals to 4, g0 is greater than equal to, I think I did the exact same thing because, sorry, okay, 23. So basically for k 2, 3 and 4, whatever this bound was, they have improved it by 2. Okay? And just to give you, one practical information that all these papers are in combinatoric courses, each other. Okay? So it's, and they're big because the technique is big. And all these uses a technique called potential technique, which I am going to teach in the next lecture. So it is an extension of discharging method. So discharging plus potential, this is what I am going to do next. Yeah. Yeah, so you can maybe come here or take your phone and zoom, see the numbers. Or they have written them, right? Okay, good. Now the last one. Last one is, where did I write it? Yes, yeah. So, G is K critical if chromatic number of G is strictly greater than k minus 1, but chromatic number of H is less than equal to k minus 1 for all, and using this notation, that means proper subgraph of G. Okay? So G itself needs k colors. It cannot be colored with k minus 1 colors. But if you color G minus anything, any edge, any vertex, anything, then the chromatic number, so if you delete anything from G, the chromatic number drops. And it becomes k minus 1. Okay? Second, F K N equals to minimum number of edges in K critical graph on n vertices. So I define a function fkn, which is you take all the k critical graphs and look at who has number of vertices equal to n. Among them, whoever has the least number of edges, that is your fkn. But why is this? It's difficult to remember this way. So what they are trying to say is, you see, if your graph is very sparse, it's easier to color. You need less colors, usually, like very crude intuition. So what they are trying to say, if I can find a bound for this value, then I know, if you give me a graph and say it is 10 critical, okay, then I know it must have a big edge density. The edge density should be higher than certain number. Okay? So, in other words, if you give me a 10 colorable graph, then I know maybe the graph is very sparse in global sense, but locally inside this there is something which is this critical graph which has high edge density. Okay? Otherwise I could have colored. So once you prove this kind of theorems, you can use them to prove a lot of other things. Maybe I will shorten a bit here. So it's the same line. I'll just say tell you a few conjectures here. That's all. So maybe I just tell you the Or's conjecture. So, which is the objective. There are many in the same line. Or's conjecture, which says if k n plus k minus it looks very strange, okay? I agree with that. And f k n, it's a recursive formula. K minus 1 by 2 and k minus 2 by k minus 1. Okay, so I will just translate this when k equals to 4. So the same thing for k equals to 4, that will look much better. It says that number of edges in any k critical graph is more than 5v minus 2 divided by 3. Okay. So if you fix one k and try to translate this conjecture in that terms using the recursion, trusting the previous values, then it will tell you if you have a critical graph, k critical graph, let's say 4 critical graphs. So what are 4 critical graphs? Those need 4 colors, but if you delete anything, it becomes 3 colors, right? So let's see, what are 1 critical graphs, which need 1 color, but if you delete anything, it doesn't need any color. Just k1. What are 2 critical graphs? Just k2. That's all, nothing else. What are 3 critical graphs? Exactly. So only the odd cycles. Because if your graph doesn't have an odd cycle, it is 2 color bipartite graphs. Right? So we know the characterization of all 3 critical graphs. That is exactly the odd cycles. So the first non-trivial case is 4 critical graphs. It is not a characterization, but it is somewhat a big information about its edge density. So I'm saying if my graph is 4 critical, then it must have a lot of edges, and lot means 5v minus 2 by 3. See.
So V is n.
V is n, yes, number of vertices.
This is for k equal to 4?
Hmm?
This is for k equal to 4?
This is for k equals to 4. Okay? And both these, so this one and this one, almost, okay, almost, is proved by Kostoshka and Yancey in 2016. And those 2 papers are kind of the beginning of this potential method. They started this potential technique, used it to prove them. So by almost, in the sense that they did not prove for everything, they proved for some things, okay? So, some values, and for other values it's almost right but not. Or in an asymptotic sense it's proved. So there is some openness there. However, this one is completely proved. And not only that, very surprisingly, after proving it for k equals to 4, using that result, you can prove the Grotz theorem as a corollary. Okay? It's not so easy to see, but you see that Grotz theorem also kind of deals with 4 critical graphs. So what this says is, there does not exist any 4 critical graph which is triangle free planar. Yes. Yes, I do. So, okay. So, what does Grotz theorem say in another words? So, what is Grotz theorem? It says that triangle free planar graphs are 3 colored. In other words, if you take a 4 critical graph it cannot be triangle free planar. This is the other statement of Gauch theorem. Why? Because you take any four colorable graph, you want to say this cannot be a triangle free planar. Any four colorable graph, you keep deleting things until it stays four colorable. There is one stage where you will reach, after deleting something, that whatever you delete, it becomes three colorable. So you take a four colorable graph, I will repeat this a bit. You take a four colorable graph, look, if you can delete something, some edge or vertex, so that after deletion it still remains four colorable. If you can do that, you do that. Okay? At some point of time, you will not be able to do that anymore. So whatever is left with you is a four critical graph. But if you delete vertices or edges in a triangle free planar graph, it still remains triangle free planar. Okay? So if my theorem were false, if this statement was false, then there would exist a four colorable graph which is triangle free planar, and from there I would be able to get a four critical graph which is triangle free planar. Okay? And that one, I know, if I have a four critical graph, it has certain kind of a edge density, edge vertex ratio. This doesn't directly give it, it's a half page proof after that. But from there, somehow I can deduce that my graph will be, this cannot happen. So then we prove the Gauch theorem, but that comes later. So I've told you a lot of things, but it's mostly history. It's history of mathematics, but now tell me if you have some questions, and then we will go to the next thing, a bit more technical.
Is homomorphism anywhere related to the minor graph?
There is a relation, but I may not go there. I just gave this homomorphism because to say these conjectures, and the improvements are almost done with potential method, so wanted to show you the strength of the technique, so that you want to learn the technique. But what I will do is I will do this proof in next lecture. This is using potential method, and from there hopefully imply the potential. But the potential method I will do very nicely, so you can actually use it later. Yes?
When is this? Or's result? When is it? 5b
Or's conjecture.
No, the 5b minus 2 by 3.
Oh, this is 2016.
Okay.
It's not Or, it's Kostoshka-Yancey. So Or's conjecture they solved for almost all cases, and they have a separate paper to explain the potential technique in a better way, which is just for k equals to 4.
And this one was a simple edge calculation, right?
From there, not really. They actually take care of the force cycles in some way. And so they kind of...
You will get an upper bound on the number of edges here.
We will, but it will not take care of the force cycles. It will say that girth at least 5 will be. But then you will have some 4 faces, and they will somehow handle that. There is a small trick. But more or less like that. Okay? And most of these things, these are typed. These edge density bounds. So, Flohan spoke about average degree, and he said, even if you have less average degree, you may have some part of the graph which is very dense, and other parts are like very loose, so very sparse. So together you have an average degree. There is a concept called maximum average degree, which says all parts of the graph is sparse if you have a less maximum average degree. For critical graphs, if you look at average degree, it kind of gives you the what do you call it? Maximum average degree. It's a intuitive. It's a little vague. What I say. Okay. It's not exactly like that, but it kind of happens like that. Okay. Because in critical graph, every useless things are gone. So it kind of the average degree for critical graph is a good sparsity parameter if you are considering with respect to criticality. So that's why this is average degree. Because you can do 2e, then it becomes degree, and then you can divide by v and it becomes average degree. So this is edge density or average degree, however you see. Okay. So I have a few minutes, but let's take a small break. Okay? Then in 10 minutes maybe I will say something. Or we can, just a second. Small break here only, and you want to break? Okay. But there is no tea or coffee. So. And then you can go for early lunch. So it is this whole thing. So there were 4 stories here. One is about this 4-color theorem and associated things. Then there was one with Brooks theorem and how it has evolved to give you these kind of results. And so basically people are not trying Brooks theorem now, they are trying this instead, which approaches to the Reed's conjecture. And then there was another story about Jessier and Jessier-GIAN conjecture, which is about circular chromatic number. And the third one was about edge density, which is Orr's conjecture. So there are 4 verticals, and in all 4, discharging and potential methods are important. And probabilistic is also important. This one is more about probabilistic method, but I wanted to have it. I like Brooks theorem. Sorry? How long? They are very long, yes. And they are very precise also. I mean, they don't explain much. So you read one paragraph, it's like a lemma for you, and you have to prove it. So it's a good idea to read with someone. Okay.
So apart from odd cycle or complete graph, do we have some critical graph?
So odd cycles are the only 3 critical graphs.
Yeah, but
Yes.
complete graphs, they are the critical graphs because every.
Yes, complete graphs are also critical graphs. So 4 critical graphs, you have a lot of 4 critical graphs. And in fact, there are infinitely many which attains that bound for 4 critical graphs. This bound.
The minimum is what?
So there are infinitely many 4 critical graphs which has these many edges, 5v minus 2 by 3. But that is a construction. I will try to explain in the next lecture.
Every 4 critical graph is a subgraph as a 4
No. Even the Misalsky graph that I drew here, like this 5 cycle with some copies
but it
and.
contains an odd cycle. Apart from like the graph does not contain an odd cycle as well as a complete graph.
No, if it doesn't contain an odd cycle, then it is binary. It is two colorable.
Yeah.
You have to have odd cycles.
Okay.
So anything which needs 3 or more colors, you need to have odd cycles. So in fact, the whole coloring theory you can think of, if you understand perfectly, if someone can understand, you have a superpower of understanding that how odd cycles interact in a graph, they know everything about coloring. So it's about how odd cycles are interacting. Okay. So even the odd cycles, if they are disjoint and very far, then it's easier to color.
Yeah.
There are theorems like that which says. Okay. So I will erase it. That's a difficult job taking. So till then you have break, 2 minutes maybe. And I think since most of you are PhD students, you want to know these research areas. You know, these are big areas and there are so much to learn and contribute also. These are really happening areas, all four. Okay. Now let's go to something kind of simple. Simple in the sense, elegant proof. By the way, who knows the proof of the 5-color theorem? Who of you know? Okay. Please raise your hand higher. Okay, not many. Not many. Yeah, I mean, you know, right?
When I was a student, I knew.
Okay.
I forgot.
So, I wish this board one day. So you know, like 2 months ago, some famous researcher claimed the 4-color theorem to have proved, like 6 pages proof. And by the time I was in a car, I was driving, and Dibbayan called me. So it's our collaborator from Leeds University, and said, you know, someone did this 4-color theorem, and he's quite a well-known researcher. By the time I came home and wanted to download it, they have retracted the paper, saying that someone has found a bug. But I could get a glance of it, and they were proving it using the dual version with edge coloring. So it may be pretty interesting. I mean, he is actually a very excellent researcher, so of course it's a bug, but it's not a very dishonest effort, you know. He genuinely thought, so it must be a very small bug. Maybe fixable, I don't know. So proof. Graph is 5-colorable. So what we are saying is, you want to prove is, you give me any planar graph, it is 5-colorable. Let H be a minimal counterexample. Okay, so proofs will be mostly pictures. Please interrupt me, ask me anytime you have questions. Yes, I'm with that. So, what I'm saying is, suppose that the theorem is false. Okay? So there will be some planar graph which is not 5-colorable and there will be more than 5 colors. Look at all these graphs. Take something which has least number of vertices. Okay? So that also means if I take this graph and do some contraction or delete one edge, okay? Delete one vertex, then what is remaining is 5-color. And I'm going to use that. Right? Is that clear? No? So, I'm proving by contradiction, first of all. I'm saying, let's say my theorem is false. What is the claim? I take any planar graph, it has to be 5-color. But I'm saying, suppose not, then there exists some graph which is not 5-colorable, but it is planar still. And among all such graphs in the whole world, I'm taking one graph which has the least number of vertices. So there is no counterexample to the theorem which is smaller than this graph. Okay? There may be other graphs which are still not 5-colorable, but they have the same number of vertices. That is possible. But if I have less number of vertices, planar graphs, then definitely that is 5-colorable.
Would this be mapping on vertices or both?
Just vertices is good enough. Okay. Now, I'll not do this. I'll come here. Okay. Prove a level. Or I will actually call it a proposition. So Shomindra, can you please help me? I know you remember these kind of things. 3n minus 6. 3n minus 6. Okay. So we want to prove this for any planar G. So by the way, you take a planar graph, the faces may not be a triangle always, right? But you can keep adding edges and make all the faces to be triangles. That is called triangulation. So usually I handle that this kind of, so there is these kind of things I handle by triangulation. So actually you take a triangulated planar graph, you will get an equality here. And if you prove that it is equal for triangulated planar graph, then you have proved this inequality for all planar graphs, right? Because any planar graph you can triangulate. So any planar graph has a super graph which is a triangulated graph. And you can just do a super graph, but spanning super graph, if it makes sense. We're not adding vertices.
You want this for n at least 3, right?
Or what happens for n equals to 2? Yeah.
It's an edge.
So n will equal to 3. Yes.
You also want to say simple, I suppose.
Simple is always same. I mean, in the beginning I have declared all graphs are simple unless I say. So only in Euler's formula I have used non-simple. Okay. So let's see. Take any planar G with n is the number of vertices, n greater than equal to 3, and actually planar G, and either I triangulate G or let's triangulate. G to get. So I have done some triangulation of G, I have gotten G hat. Now I will work only with G hat. So in G hat what happens? So every edge is part of two faces, right? So if you stand on the edge, one side you will see one face, another side you will see another face. So every edge is part of two faces, and every face has how many edges? 3. So if I am counting all the edges on the face, then I have counted it 2 times. If I count all the faces, then I have counted 3 times. So 3f. Okay. And then I have the Euler's formula. V minus E plus F equals to 2. So let's, which one should I replace? I want E and V, let me just make all of them V. Makes more sense. Okay, so F we have to replace because I want E and V there.
Actually, E is you are bounded by 3 by E.
3. Say it again.
E is lower bounded by 3
Yes.
by
Yes.
3 by E.
So F is equal to 2E by 3.
This can be dash by 3 because E is better than.
Okay, okay, that we can do. E dash by 3. So E dash equal to edges of G hat, and E is edges of G, and then this is bigger. E dash is bigger. Let's remember that. Okay, now if I replace it, what do I get? V minus E dash plus 2 E dash by 3 equals to 2 and multiply by 3. So yeah, I think you have that exactly. But please check. Minus 3. So it will go prime equal to 3v minus 6. Okay? But then I also know E is less than equal to E dash, so I have this. Okay? Is that okay for everyone? For proofs I will ask once more. If it is not, I will repeat. I am not writing down everything, so it's just calculation. Yes? So the crux is this. Once you know this, you know everything else. No, also the outside face is triangle now. So you have triangulated. So if you take a cycle, if you take a 5 cycle, and you want to triangulate it, so what you can do is you can add things like this. So inside everything is triangulated, but you have to make more triangles. So now you see it is a triangle also. So now the triangulation is complete. Okay? So you keep adding edges until you get triangle, but if you have a face which is not a triangle, you can add another edge without making it like violating the planarity. Right? Okay. So that's why this works. So if you just, for each face there are 3 edges, but when you do that, you have double counted the edges, right? So that's why 2e prime equals to 3f. Plug in the Euler's formula, you get this. How did you get e prime? By adding edges. So e is less than equal to e prime, and that's why you have this inequality, which is that. Okay. Is it 10? Almost. I think I'll not be done with the 5 color theorem, but one more machinery I need. So, we like permutation and combination. A trick question. You like, I know. You have the games, right? No, one of you. Yeah. Yes. So, there are 99 people in the room. Now, they will shake hand with exactly 9 other people, each of them. In how many ways can this happen? You cannot answer. You should not answer, in a sense. So in how many ways can this happen? There are 99 people in the room. Each of them can shake hand with 9 people. In how many ways can this happen? So if I shake hand with him, sorry, my hand is full of chalks. So then I have shaken hand with one person. He has shaken hand with one person. So now let's count how many number of handshakes has happened. I have shaken hand with 9 people, right? Each of the 99 people have shaken hands with 9. So total 99 handshakes, but our handshake is counted 2 times. When I counted 9 for me and 9 for him. So total number of handshakes should be this, which is impossible. So the answer is 0. Okay? This exactly is the handshaking lemma, which says summation degree V for V in Vg is equal to 2 times the number of edges in G. You know? So basically you are counting the degrees of the vertices, adding them up, but in this process you have counted each edge twice. The edge between me and Supraja, once you counted my degree, it is counted once. When you counted her degree, it is counted the second time. So you have counted it twice, so it is twice number of edges. Okay? So from here what I can get, now time for a corollary, and I will end there. Time for a corollary, which is 2e equals to summation degree v in the vertices is less than equal to 6v minus 12. Now I divide the whole thing with number of vertices. Okay? Oh, sorry, I should write x here. X. So 1 by v summation degree x in v is less than equal to 6 minus 12 by v. And okay, this is some positive quantity. Okay? So what I can say, I can forget about this part and say this is a strict inequality. Right? So I know the average degree is strictly less than 6. So there must be one vertex which has degree 5 or less. Okay? For all planar graphs. So subgraphs of planar graphs are also planar graphs. So that means the degeneracy of planar graphs is 5. Okay? So here, with this corollary, I have one more corollary that planar implies 5D degenerate. Okay. So we stop here. Okay. It's 1, I think. And we regroup at 2:30 because 1 hour is. So every day we will regroup at 2:30. 1 hour is too less for everyone to come back. Okay.
Maybe you can say that you just proved the 6 color here.
Yeah, but 6, 5 together maybe. I have to say about degeneracy and this ordering. It's already 1. Yes, exactly. Okay. Or maybe in the tutorial.